Hello and welcome to this webinar from the U.S. Department of Energy Solar Decathlon. My name is Michael Young. I'm the Assistant Competition Manager for the Solar Decathlon Build Challenge. And today in this webinar, we're going to be talking about the new Embodied Environmental Impact Contest. And we're going to share some best practices and suggestions and advice for you to succeed in this contest. Through this 20 to 30 minute webinar today, we're going to start by talking about why this contest has been added to the Solar Decathlon, the importance of looking at embodied environmental impacts. Then we'll step into talking a little bit more about what the contest entails. And finally, we'll finish with some examples of best practices and really good submissions that we received from teams in a pilot of this contest that we ran in the 2020 Design Challenge. So with that, let's begin by talking about why is this so important? Why is this being added to the Solar Decathlon right now? One of the main reasons is as we look at global emissions of carbon dioxide by sector here in this pie chart, you'll see that buildings account for the biggest piece of that pie at 39%. And the built environment is only going to continue growing. Projections show that the global building stock is going to double by 2060. That's another almost 2.5 trillion square feet of built space that requires materials, requires energy, and that is a really, really large impact on the environment that we need to think about in the building industry as we think about the design and construction of new buildings. Digging into this a little bit further, you'll see that 39% of buildings, about a quarter of that is embodied carbon. Embodied carbon being the materials that go into the building and the construction process, where the other 28% is the emissions associated with operating that building and the energy that it needs for the occupants while the building is in use. But as the operations piece becomes more and more efficient, as we get better with energy efficiency, designing the building to operate and use less energy, that embodied chunk of the pie is only going to become more and more important. And this is one of the main reasons that this is being introduced to the Solar Decathlon at this time. For a long time, Solar Decathlon and the buildings industry in general has focused on that buildings operations piece of finding ways to make the building more efficient, get it to net zero energy consumption. But now we want to also think about that full life cycle of the building from what's called cradle to grave, and we'll get to that term later. But all of the materials that go into a building, the construction processes, and then what happens at the end of its life. This is also important to talk about that overall embodied impact of a building. So some terminology that you'll see as we talk about this, three main terms you'll hear are circular economy, embodied carbon, and embodied energy. And this slide is just a quick rundown of the definitions and kind of how these terms are used. But there's a lot of other information out there that you can find in various publications and other resources. But generally, circular economy is just that. It's an economic system. It's a term that describes how an economy works or how it could work. It's not something that's typically quantified or measured, but rather it's a way of thinking about, instead of our existing traditional linear economy that goes from extracting raw materials to manufacturing something to using it and then finally disposing of it at the end of its life. Circular economy is all about closing that loop and bringing that end of life back into the process a little bit more, instead of disposing of things and putting those components in a landfill. Find ways to recycle, reuse, or repurpose those materials to kind of bring it back into the beginning of that circle. Now, kind of nested within this overarching term of circular economy Other terms, embodied carbon and embodied energy. Now, these are quantities that can be measured or calculated if you have the right information, go through the right processes to calculate these. And this is part of what is determined and calculated through a life cycle assessment. We'll talk about that soon as well. But part of the reason that you see embodied energy kind of nested within embodied carbon is, yes, there are, embodied carbon emissions associated with energy consumption that goes into any kind of product, any kind of manufacturing. But there are non-energy emissions of carbon and other greenhouse gases. Primarily in the building sector, this comes from the production of things like cement, where through the chemical processes of curing that cement, greenhouse gases are released, and that has nothing to do with the energy involved with going through that process. It's just the chemical reactions that occur through that, the development of those materials, and that is such a big part of the buildings industry. That embodied carbon actually comes to incorporate more than just the energy involved in producing, transporting, and using different materials. So how are we defining embodied environmental impacts? Basically, what we're talking about is the impacts associated with the various stages of the building's life cycle, excluding the operational stage. So this is, as you see here, everything from the extraction of raw materials, of those raw resources, manufacturing those resources into some kind of material or building component, transporting those materials to the construction or installation site, and then the building gets built. We're excluding the operational stage because that is what's called operational energy and operational carbon. That's what we know and what we're familiar with as the environmental impacts associated with using a building, with occupying a building, and operating it for whatever its occupants need it for. But during that use stage, during the occupied portion of its life cycle, there are embodied impacts there as well, in the replacement and the maintenance of various pieces of equipment, various components of the building, and this is everything from carpets and floor tiles to mechanical equipment that needs to be replaced or maintained over its life. This is part of the embodied impact of a building. And then finally, at the end of the building's life, looking at the demolition process and what happens with those materials at the end of life. Now, looking at this a little more formally, going into a little more detail, this is that same kind of life cycle arc, but this is defined by a European standard, standard 15978, as you'll see in the bottom left corner. You can find this online, but this graphic I think is really helpful to show the various life stages, how they break down, and where that boundary is drawn for embodied carbon, for what they call whole life carbon of the building, and then anything that's kind of outside that scope or beyond the life cycle. So starting here on the left side of the diagram, you'll see the blue and the green outlines for the various life stages, and keep these in mind, and notice that the green one, the embodied carbon, excludes the operational energy use portion of the building's life cycle, as we mentioned on the previous slide. But the blue outline, the whole life carbon, does include that, the operational stage. But inside of all this, you'll see from A1 through C4 are the various life cycle stages, as we look at, again, supply and extraction of raw materials, transporting those materials to a manufacturing stage, transporting them again once they've been manufactured into construction components or building elements, to stage A5 there, which is the construction or installation process, stepping then into the use stage, the embodied carbon and energy associated with that, with the use of the building, the maintenance, repair, any refurbishment or replacement of materials or components over the life of the building. And then into stages C1 through C4 is, as I said, that end of life stage, the deconstruction or demolition, transporting those materials to wherever they're going next. If it is to a waste processing plant or to a landfill, that transportation of those components gets included here. And then finally, disposal. And what you'll see here on the far right side is it's kind of looking beyond the life cycle. It's beyond the scope of embodied carbon, of whole life carbon. But this beyond the life cycle piece is really that circular economy portion we talked about. How do we, in the buildings industry, think about the benefits beyond the building's life cycle? How do you reuse, recover, recycle, repurpose materials from a building? As I mentioned, closing that loop, bringing those materials back into this process so that as another building's life cycle begins at A1, there are fewer raw materials that need to be sourced, and they can come from that stage D, the beyond the life cycle stage of another previous building. If you kind of multiply this and expand this across the entire building sector and the entire economy, you'll see that there can be a huge impact to reusing and repurposing these materials and really thinking holistically about this life cycle when a building is designed from the beginning. So this is a very important diagram to consider, to think about as we look at the different life cycle stages, as we think about what's called a cradle to grave life cycle assessment. Cradle to grave goes from stage A1 all the way to C4. It includes all of these life cycle stages, and it doesn't leave any piece out except for maybe that operational carbon portion. But another term you'll hear is what's called cradle to gate. Cradle to gate is only stages A1 through A5, basically everything up to the end of construction when the building becomes occupied. So these are some terms to be aware of and to be careful about as you're completing this contest for the Solar Decathlon and as you're looking into the life cycle assessment of your building. Now, speaking of the Embodied Environmental Impact Contest that is being introduced here to the Solar Decathlon, these are just a few bullets explaining or summarizing the components of the contest, what you will be asked to do as competitors in the Solar Decathlon. A full write-up of this contest is available in the Solar Decathlon rules, but generally this contest is going to include a life cycle assessment or an LCA of your building's environmental impacts. And for sort of a narrative and analysis portion, we're going to ask teams to discuss the assumptions that are made for this life cycle assessment and the various kind of baseline or boilerplate type of information about your building that goes into this LCA. And then from there, we'll talk about examining your different design decisions and material selections with regard to circularity and the embodied environmental impacts. What caused you or motivated you to make certain decisions or select certain materials as you look at the full life cycle of a building. And then finally, there are going to be trade-offs between the embodied environmental impacts, that upfront portion, versus the operational impacts of your building. And we want you to talk about how those trade-offs were evaluated and how you weighed the pros and cons there to make your final decisions and determine the the optimal design for your building. Now, to perform the life cycle assessment, there are a variety of tools out there that are available. They come in various forms, from online to downloadable software. There are free versions, there are paid versions. You are free to use whichever LCA software you choose. But the Solar Decathlon does have a preferred LCA tool. It is called One-Click LCA. It's a web-based LCA tool, accessible online. There's no download required, and there's a free license available to Solar Decathlon participants. Some of the reasons that we at the Solar Decathlon do prefer this tool is it has a cradle-to-grave lifecycle scope, as we had mentioned, going all the way from stage A1 through C4, looking at the entire arc of a building's life. It reports on embodied carbon, embodied energy, and other environmental impacts. It even has a circularity tool, a circularity metric, to look at how the materials that you choose could be recycled or repurposed at the end of life. And there are a couple ways that this tool can be used. You can do manual entry of material quantities and the types of materials that are used in your building, or it can take an import directly from a variety of BIM models. I know there's a plugin with Revit that allows you to import your design directly into One-Click LCA, and it populates all those material selections automatically. Separate from this webinar, I'll mention that there is a tutorial from One-Click LCA that we've made available to you as well that specifically talks about this tool and some tips for how to use it, walking you through the various steps and some instructions for getting started with One-Click LCA. Now, we're going to close today's webinar by looking at some great examples of best practices in the Embodied Environmental Impact contest that we saw when we ran a pilot version of this contest in the 2020 Design Challenge. This was an entirely optional contest for teams to participate in, and as we reviewed the submissions we did receive, there were some really great examples that we wanted to share with you and show you what we think are some great ways to succeed in this contest. So first example here comes from the University of British Columbia, their third quadrant design team. And the best practice here is define your scope and your boundaries of your LCA. This is really fundamental and foundational to the success of this contest. As you look at the scope of your LCA, tell us, what components of your building, what building components are included in the life cycle assessment. Is it the entire building, including finishes and furnishings inside the interior when the building is complete, or is it does it exclude those things? Is it just the structure and the mechanical, electrical, plumbing systems that are installed? Where is that line drawn, basically? And then next, what is the time period used for the life cycle part of the life cycle assessment? Does it match the expected life of the building? And if not, why? What is the reasoning for choosing a different lifespan for the LCA versus the lifespan of the building? And then as you talk about the boundaries of your life cycle assessment, what life cycle stages does the analysis cover? We've mentioned this a number of times now, but it's very important to note if you are doing a life cycle assessment that only goes cradle to gate, or if it covers the full cradle to grave scope of the life cycle of the building. And University of British Columbia did a great job of defining this in their submission and really walking through the various assumptions and details of their life cycle assessment. Another example here from that same team at the University of British Columbia is about justifying your decisions and discussing the trade-offs that occur as you make decisions between embodied and operational environmental impacts. This is a really important narrative and really helpful narrative to show us, what motivated your design decisions and your material selections. Were multiple options analyzed for their life cycle impact before selecting one, or was just the first material selection or design decision made without considering others? Walk us through that process, how your team came to make the various decisions that you did, And what was the process like? Did you use an analytical process? Did you use these LCA tools to help make these decisions? And also, did any decisions actually increase your embodied environmental impacts in order to reduce environmental impacts on the operational side? That is really one of the main things as part of Solar Decathlon is, some things might not score as well in order to do well in other places, but the goal overall is to minimize both your embodied and operational carbon, not just one or the other. We recommend using the LCA process to find that right balance. So a great example here of finding that balance of making these kinds of decisions and discussing these trade-offs is in the University of British Columbia's Solis House. They talked about how they saw a large portion of their embodied carbon actually came from the material stage at the beginning of the life cycle due to their design having a really robust envelope with high levels of insulation. So this is a lot of material that's being used. It causes an impact to your embodied environmental impacts because you're using more material. But this decision was made, and they justified this decision by saying it was made to enable low operational energy use during that use stage of the building. By having extra insulation, it allowed the building envelope to perform better and use less energy for heating and cooling over the occupied stage of the building. And they even went further and quantified this decision and said, by making this decision, there was an increase in embodied impacts to achieve that decrease in operational impacts. And the overall life cycle impact was reduced from 671 tons of carbon dioxide equivalent down to 169. So this, as I mentioned, is just a really good example of justifying your decisions, talking to us about the trade-offs, and quantifying how this balance was found to look at the relationship and that synergy between operational impacts and embodied impacts and how these decisions are made. Next is looking at your specific material selections. Tell us why you chose certain materials. Discuss the reasoning behind this and how these decisions were made. And a good example here comes from Ball State University, their Temple Commons project in the attached housing division. Talk to us about how they chose structurally insulated panels, or SIPs, for their wall system to reduce their waste from cradle to grave. They cited research that said that this type of wall system really reduces the overall waste generated throughout the life cycle of the building compared to a more traditional wall system. And they show us that in their analysis by specifying that less waste and less embodied carbon and embodied impacts associated with that waste is generated over the life cycle, and specifically at that end of life, as these panels are able to be disassembled and reused or recycled or repurposed in some way. The next suggestion here, the next really good example that we saw in the 2020 Design Challenge pilot version of this contest was Ryerson University did a really great job showing a comparison of their designed building against a minimally code compliant baseline version of their building. So it was their same building, but only if it had been designed just to meet code. That base building doesn't go above and beyond and make all the same designs decisions that their building made, but it shows specifically where improvements could be made over the life cycle with different material selections at different stages of the life cycle where these improvements are made. And this is just a really great comparison, not only for the discussion portion, but for the analysis and the visuals and the quantification of how improvements were made and how this was achieved, and showing that this team and this design does go above and beyond what this building would be if it just minimally met what the code required. And the final example we'll show you here is from another project from the Ball State University team, considering the reuse of existing materials. This team designed a project that was actually a renovation of an existing structure, and they talked about how by reusing existing infrastructure on the site, they drastically reduced the amount of raw materials that were needed, or that would have been needed if you had just demolished that site and rebuilt. And they actually quantified it here on this graph by looking at embodied carbon of their proposed renovation in blue. The black line is the operational carbon per year over the life of the building. And you'll see that in their renovation process, that operational carbon comes down because they've upgraded the building, made it perform better. And then they compare that to their pink line, or that red line there, of what would have been the embodied carbon if they had demolished that building and just rebuilt. So sure, it would have been a high-performing building that used less energy over its lifetime, but all of those new materials and processes that would have been required to build a new building would increase that embodied carbon so much more than just renovating it, as you see in that blue line. So another thing to consider here is not only the reuse of existing materials, but certain construction practices and the way the building is designed can also impact how well materials can be salvaged at the end of their life. Thinking about how a building might be able to be, disassembled or deconstructed rather than fully just demolished and broken into waste that goes into a landfill. Thinking about how do you design a building from the beginning to reuse materials at the end of its life. So a couple different suggestions here in this example, but one of the main things about looking at that circular economy portion of that beyond the life cycle portion that we saw in that graphic earlier in the webinar here, looking at how did materials get reused. This is a really important example for how to consider that and how to talk about it in your projects. So that is everything we have for you here today, and we thank you for watching this webinar. And if you have any questions at all about the Embodied Environmental Impact Contest, we invite you to reach out to us at solardecathlon@nrel.gov. And as always, you can access additional information on the Solar Decathlon at the Solar Decathlon website, or follow us on social media with the hashtag Solar Decathlon. So thank you again, and we wish you the best of luck in your participation in the Solar Decathlon. Thank you.